Hi, everyone. Welcome to the seventh episode of Silicon Valley Quantum Computing Group. Today, we are going to talk about quantum applications in energy. We have with us Rima Oueid, who she's a fellow from the US Department of Energy. As always, I'm your host, Taposh Roy. I am the Director of Innovation at Kaiser Permanente. My work is mainly on digital twins, machine learning, and AI. I'm very interested in quantum computing, and hence I lead the Silicon Valley Quantum Computing Group. I'm also the author of book Medical Image Processing with Deep Learning. I'm also writing a book on AI governance, both in the classical and the quantum realm. To help me today, we have a volunteer, Divya Roy. She is a student from the Pine Valley Middle School. She is in sixth grade and she is helping us with surveys and making the presentations and all the nice things. Of course, she's interested in quantum computing and she'll support the group. Agenda today. Rima is going to talk to us about applications in energy of quantum computing, of course, of quantum. We're going to have some fireside chat with me and then followed by our audience Q&A. At the high level, the session is going to talk about the electric sector, how things are evolving, how business models are emerging, and how we are accelerating in variety of areas. We're going to talk a bit about the atomic clock. We're going to talk about, in general, quantum sensing and the communications, and how the complexity of the grid, the electric grid that we know of, can be solved by using quantum computing. With further ado, our speaker. Our speaker today is Rima Oueid. She is a commercialization executive at the US Department of Energy. She leads market development activities and bringing them into commercialization by connecting startups with the Department of Energy. She is also on the board of QEDC, which is Quantum Economic Development Consortium, and she serves as the chair there. Along with that, her background is equally impressive. She has an MBA from University of Chicago, the Booth School of Business, and she was selected as a Kaufman Fellow there. Rima holds a Bachelor's of Science from University of Illinois Urbana-Champaign. With that, I'd like to open it up for Rima to take us through her talk. Thank you, Rima.
Thank you. Thank you for the kind words and for the introduction. And good morning to all of you, and good afternoon for those of you on the East Coast, but I assume most of you are on the West Coast. So I am excited to be here today to talk to you guys about this. And quantum is an area, a passion area for me. Even though I am not by training a quantum physicist, formal training, but one of those things that has always been in the background throughout my life. So, in any case, I'll jump right into it and share my screen. Let's get that going from the beginning. All right. So I'm going to give you guys a little bit of background of my office, just really quickly to kind of give you a little perspective of where I'm coming from and what has given me the pathway to do this work. And I'm going to talk a little bit about the collaborations that we've done with QEDC in particular, because it's been helping me sort of build this this pathway to leverage the energy sector as a customer of quantum. And I'm also going to touch on some space activities that we're exploring and how it intersects with the energy sector and why it's an area of interest for us. So to begin, my office, the Office of Technology Transition, started about 5 years ago, a little bit more than that at this point. And we were tasked with helping to commercialize DOE technologies, to be able to get them into the marketplace, to get them licensed, once they've been patented and so forth. But at the same time, we realized that that's not good enough, that we have to do more than that, that we actually need to help build the market. And if you build it, will they come? Not necessarily. We learned that the hard way, particularly on the renewable energy side of things, right? Like solar, we discovered solar technology. We tried building it, they didn't come, and there was a whole host of reasons for it. And then the manufacturing really flourished abroad, right? And part of that was because in China, for example, they were also building the demand for it. Obviously, they have an easier way to do that. They're not a democracy. They just dictate. But nevertheless, the strategy worked, and that's where manufacturing is dominant in terms of solar. We don't want that to happen anymore. We learned our lesson. So we work to build market acceptance and to help accelerate commercialization of technologies in the US. And I've really been focused a lot on quantum information science as part of my portfolio. So I work on trying to figure out what the gaps and the needs are and how we can overcome those market barriers. So we also serve as a bridge to the private sector. We try to build partnerships with the labs to do collaboration work and serve as a front door. But we also work with our sister agencies to get them on board, where we find synergies. And we also try to find areas where we can do deep dives that can really sort of help move the needle and get people excited about a particular technology. So it's a lot of herding cats, especially in government, because often we rely on government to do the head banging process to get things to a place where they can then be adopted, right? So, so just that for some background. One of the things that we learned really early on is when you're dealing with a technology that is, I would say for many people, intimidating because they don't understand it, you kind of have to move away from talking about the technology and focusing more about what are the use cases, at least in terms of the narrative that you then share with the world in order to get them to take interest. You got to find out what the value proposition is of the technology. So which is very different for a government agency to do, because we're techie geeks typically in the government, right? Very linear thinkers, mostly engineering types. And it's like A plus B equals C, and don't talk to me about Z because I don't know what fits in. What I have to figure out what comes after C next. And so that vision, that perspective is oftentimes lacking. But then they bring in people like me, who that's the job is, what's the vision? Where are we going? We say these are our goals. Let's figure it out. So we have to sort of follow somewhat of a linear process to get people on board. And so working with consortium like QEDC and our industry partners, we've been piecing together the things that are needed in order to get other folks on board. And so we worked with the Quantum Economic Development Consortium to build a guide to quantum safe organizations, which also have application in the energy sector. We've then built workshops and focused on energy in particular to do optimization. And then we're also looking to expand beyond just optimization, which is focused mostly on quantum computing, but to also explore things like quantum sensing, and then also obviously security. So we have a security workshop that will be focused on the quantum energy sector, and it will leverage both, or not both, but quantum computing, quantum sensing, as well as other quantum technologies that provide security, such as quantum key distribution, quantum random number generators, post-quantum cryptography, and even just we're looking at quantum entanglement in general and how that can be used as a security feature for the energy sector. And I'll talk a little bit more about that. But this workshop is now being planned for June. We're looking at the second week of June. So if folks are interested, this is something we are opening up to folks outside of just QEDC. But we are looking particularly for folks that have an energy sector perspective to bring to the workshop, because we're building this workshop such that it will allow us to blend different folks and different types of personalities together. And I'll talk a little bit more about that in a second. And then lastly, we are exploring quantum partnerships to do space demonstrations, and I'll talk a little bit more about that. So this quantum energy workshop that we already did last year was a great example of collaboration across various types of backgrounds and industries. Well, not industries, but perspectives. We brought in the national labs, we brought in the utility sector, and then we brought in the quantum industry sector. QEDC was the host, Accenture was the facilitator, and this was done in collaboration with DOE. So I'm a member of QEDC, so I helped, obviously put this together. And we had a phenomenal turnout, and we had over 90 participants, and we were trying to keep it small, so that we could actually blend different types of people into the breakout groups. And so our thinking was, we know that the grid is becoming increasingly complex. The grid, we claim we want, is going to be a smart grid. This means that it is essentially going to have to move away from the spoke and wheel model that we currently exist in, or that we originated in, rather, into this two-way flow network. And it's not just going to be a two-way flow network for electrons, but for data as well. And so it becomes very complex. And much of this activity is happening at the grid edge. So at the grid edge, there is immense amount of analytics and data that has to be managed. And part of the hesitation from the perspective of the utility as to why this hasn't happened, and some would argue they're even creating roadblocks deliberately, is because they don't feel comfortable managing all that data that is happening at the grid edge. They want it to be somebody else's problem, or not a problem, right? And I think that's the preference. But nevertheless, we are moving towards that, whether they like it or not, because of distributed energy resources that are connecting at the grid edge, and because of electrification of transportation. So in this workshop, we developed a matrix to look at the different areas within quantum that would apply, and also the different ways that we look at the energy sector. So we sliced it into these columns to look at what is the perspective of the customer or the asset owner, which is typically at the grid edge, right? What is the perspective of the aggregator, which might help alleviate some of the concerns of the utility. But also it could be the pain point for the utility, and I'll explain that in a minute. Then we've got the distribution utility, right, that we all know and love because they're the ones that send us our bill. And then we've got the transmission system, and then the generation system at the end. What we realize is that these perspectives vary significantly. Most of the energy markets today exist within the transition system. It's the energy markets, the bulk markets. They call them the wholesale markets. And they're managed by oftentimes an ISO or an RTO, which is a transmission operator, essentially. And they are, for the most part, more lean forward on some of this stuff than the distribution utility, which is who you actually interact with the most as a customer, right? And so what is lacking is a market at the distribution level, because at the end of the day, as you realize, most of the activity is at the distribution level. That's where the transactions are actually happening or could happen at scale. That's where the electron exchange is happening more and more every day, and where the complexity really emerges from. So B, the aggregator, the service provider, if that role evolves properly, then they could actually help become a conductor of all the activity that is happening on the customer side as it integrates with the distribution network. And this is where I think there's going to be a huge role for something called virtual power plant providers. So I really see them as becoming customers of quantum technologies, as well as the utility industry. But I think the innovation is going to happen amongst the aggregators, who are most likely going to be the adopters of some of the quantum computing capabilities to really optimize the grid. So one of the things that came out of this report that we did last year was, we were focused solely on grid optimization. And so we were only looking at quantum computing. And what we realized from the ideation process that we did with the participants was, fault tolerant prediction became a high value use case. Where the majority of participants saw opportunity in the near term with respect to quantum computing. They also saw energy market optimization as another opportunity. Now, granted, remember what I said earlier, the wholesale markets occur at the transmission side, so they're clearly customers, but they could also be at the distribution side. And the ultimate goal and vision is to be able to integrate the distribution system with the transmission system in terms of energy market activity. That is essentially going to be the holy grail for a fully optimized energy market. Another important high value use case was integrated planning and optimization for reliability and resiliency. This is where those annoying distributed energy resources, is from the perspective of the utility, and electrification of vehicles comes into play. Electric vehicles today, for the most part that are available in the market, are unidirectional. But as for some of you that don't know, GM and Ford, Honda, and Nissan, they all have started developing, if not have already developed and commercialized, bidirectional electric vehicles. And I established a partnership agreement with them to work with DOE to help bring this to scale, which basically means that electric vehicles are going to be putting power back on the grid. And for those of you that may not appreciate this, the Nissan Leafs today that are on the road represent more, and they're all bidirectional already. And they've been that way for more than 10 years. The Nissan Leafs alone that are bidirectional on the road in the US today, their battery capacity already exceeds all the stationary battery storage that is interconnected to the grid today. And when you think about where electric vehicles are going, the IEA, the International Energy Agency, has forecasted that by 2030, the amount of electric vehicles that will be on the road will have 10 times the amount of capacity that the grid is projected to need at that point in time. So you could just imagine the amount of capacity that electric vehicles bring to the table. But where are they going to interconnect? It's going to be at the distribution system. And that is bringing major heartburn to the utility industry because they have no clue how they're going to be able to optimize for that. Now, the bidirectionality is a asset to the grid, whereas if it's just unidirectional, it's pure load. Believe it or not, that freaks out the utilities even more. That makes them more concerned because it's going to be zapping the system. So this is creating pressure on the utility industry. And this is what is also creating opportunity for quantum technologies to be able to solve for that problem and optimize for it. And then obviously the quantum chemistry simulation for new materials, like for batteries, is also a very interesting opportunity. Now, from a quantum standpoint, quantum computing standpoint, there's different types of problems that quantum helps address. There's combinatorial optimization, differential equations, linear algebra, factorization. The near-term application is actually combinatorial optimization. That addresses the traveling salesman problem. And so from a DOE standpoint, this is where we see opportunity for quantum computing to solve this distribution level system problem that we have, the optimization problem. So the McKinseys of the world, the Bains, and everyone who's pontificating on the market opportunities for quantum, they're really focusing on the stuff that they understand and where people are already investing. So it's often from the standpoint of the financial sector and from pharma. They're sort of forgetting about this energy piece, right? And the other thing that energy provides is an opportunity for us to not just leverage combinatorial optimization problems, but some of these other more complex math problems that require heuristics. So oftentimes we hear that, oh, quantum computing is not going to be practical because they're noisy. They're full of errors, and we have to do this error correction and so forth in order to get the precise answer. The energy industry, when we do contingency analysis, we do it based on heuristics. So we're not looking for a precise answer. We're looking for a range of probabilities. And so those noisy intermediate scale computers actually are already useful for us. What we're lacking is the algorithms. And that's where we need investment. It's in the algorithm development side for contingency analysis, as well as algorithm development for the optimization piece. And in terms of optimization, I think we could do a lot with just quantum annealing. So that jumps over. So just keep that in mind. That's so from a computing standpoint, quantum annealing, which is already commercially available, has application. We need the algorithms. From a noisy intermediate scale quantum computer, which is supposed to be the stepping stone to the fault tolerant quantum computer that can answer the fundamental laws of nature, that NISQ computer today has application and value. And we've done some preliminary analysis to demonstrate that relative even to classical computing and high performance computing. And so we need to do we need the algorithms, and there's obviously a lot of work that needs to be done to make that happen. I also want to hone in on quantum sensing. It sort of kind of gets forgotten about. And what's interesting is that quantum sensing has been around for 20, 30 years. We use it in atomic clocks. And it's also used in MRI machines. So we've commercialized it, but in very few areas. And also we've commercialized it, but maybe we haven't commercialized it in the best way. So in terms of atomic clocks, we use them in GPS. It's the reason we have navigation systems. But GPS is not reliable, and the grid has many areas that are GPS denied. And also GPS is easily spoofed and jammed. So from an energy standpoint, it's not reliable. It's a vulnerability, but yet we need timing. And as you heard me talk a lot about electric vehicles, if they're going to become assets to the grid, then we need electric vehicles to be synchronized with the grid. And so that P&T piece becomes even more important. Do we really want to depend on just GPS, which is easily spoofed and jammed? We know that there are suitcases that could be brought to an area that can easily deny and jam GPS. And so the military is very much concerned about this. Now, you can imagine a malicious actor easily being able to turn our grid upside down as it becomes more and more complex. So although I'm advocating for complexity for the grid, at the same time, we're also thinking about how to mediate the vulnerabilities that can also come with that complexity. And so this is where I think quantum sensors really bring a lot of value, because they can be deployed directly on the grid and in vehicles. So they don't have to depend on GPS, and it makes them more reliable. So there is a huge opportunity here from a quantum sensing standpoint within the energy sector, and also with the assets that they're going to be interacting with, like solar farms and wind farms and electric vehicles. So we ran this quantum sensing workshop last year that focused specifically on just sensing broadly, just to look at it at a high level standpoint, to understand, what are the types of sensors that are out there today, and what can they do, and what's their maturity, and what are some of their applications, and what are they competing against. And so timing really obviously stood out, and I kind of really focused a lot on that just now. But there are other types of electric or different types of quantum sensors that are also available that have value in the marketplace. And from a energy standpoint, we're realizing that not just timing, but these other types of sensors could be used on the grid to measure and detect anomalies. So it's part of our security capability. It's part of our resiliency capability. And so what we're looking to do is have another workshop coming this fall that focuses specifically on quantum sensing for critical infrastructure. And what's interesting is transportation is also interested in this, because these sensors could be used on the grid. They could also be used within the transportation network as well. Think about anomaly detection for bridges and roads. That will give us insight into how how our infrastructure is able to maintain itself. And so there's lots of various opportunities here for quantum sensors to do anomaly detection on all kinds of critical infrastructure. But energy is obviously interested in this from in managing the grid. The other area that we see quantum sensing really play a role is in terms of exploration, and I'll get into that a little bit more. So this is just kind of a quick overview of atomic clocks and the priority use cases that we have found. But some of these sensors can also be used to do exploration, energy exploration. So we could do more precise exploration for oil and gas, so we're not fracking everywhere, and also we can find geothermal and areas underground where there are caverns, so we could store carbon, as well as where there's water, where we may not have otherwise thought to look. Really interesting opportunities for quantum sensors. This just highlights some additional priority areas for different types of quantum sensors. I mentioned mineral exploration, which sort of touches on why we're interested in space. So you can do mineral exploration on Earth, but you can also do it in space. So I'll talk a little bit more about that in a second. Another thing that these sensors can help us do is also, look underwater and be able to know where we would want to site, for example, wind farms. And obviously DoD is interested in this in order to detect ships and things underground, but this is also going to be very useful for offshore wind siting. As you can imagine, it's really expensive to have to send people underwater and be able to scope out where they can site these offshore wind capabilities. But some of that same technology that we're using for brain imaging and biomagnetics potentially could also help us site wind farms. So a lot of really exciting opportunities here for energy for the same types of sensors that are being used in medicine. So this is just a highlight of sort of where the projected impacts for national security of quantum sensors are, and so it just kind of gives you a sense of where they fall in terms of value and maturity. And so there's a lot that's already commercially available that we could use today in terms of chip scale atomic clocks, magnetometers, and gravimeters. This is just another perspective from for the private sector that could also leverage quantum sensors. So some very similar and lots of overlap here. And that all came out of the workshop. And I'm happy to share the link to the report that came out of both the quantum sensing workshop from last year, as well as the quantum energy computing workshop. So my office is also, as I mentioned, developing public-private partnerships, develop commercially available space-based quantum computing, sensing, and networking systems. We want to show the viability of this. And so we, from an energy standpoint, see value in secure communications. And we're working with DoD in particular because we see synergies there. NASA's also involved. And we're looking at ways that we can leverage each other's expertise and capabilities to be able to demonstrate how we can leverage quantum technologies in space. So these are just kind of some of the high-level activities that we'll be pursuing. DoD in particular is very much interested in putting data centers in space. And there's value for that for some of their mission activities. There's also value in having that happen for us, from us being energy, because of what I'm going to tell you next. So I touched already on how quantum sensors can be used for surveillance in orbit. You could see this obviously from a DoD standpoint to see underwater, anomaly detection, situational awareness, but I also mentioned, exploration of rare earth minerals and water. We can do that exploration on Earth, but we can also do that exploration in space. And you can imagine the value in and the interest in being able to explore minerals in space. So knowing which asteroid, for example, might be worth focusing on and sending resources to extract valuable resources that we could use on Earth, and maybe discover resources that are going to be of greater value than what we have here on Earth. I mentioned position, navigation, and timing. We can deploy these things here directly on assets in Earth, but then obviously if we are looking to explore minerals in space, we're going to need position, navigation, and timing on the technologies that we're using in space to do that type of activity. And I think this is really exciting, and being able to piggyback off of work where we find synergies with DoD is a great opportunity for us. And then I also mentioned secure communications. We need that on Earth, but then obviously if we're going to be doing exploration in space, we're going to need that secure communication in space as well. And this is where quantum random number generators come in as well. I'm not sure if people appreciate this, but most random number generators that are used today for encryption keys are not truly random. They're based on classical computing. So this is why they are hackable. And actually, I'm going to go back to a previous slide where we talked about the different types of algorithms. So, factorization here is at the bottom because of the type. This is the reason that the administration, well, for those of you that don't know, the president put out a memorandum last year and then signed into bill an act encouraging the federal agencies to all prepare against a quantum threat. And that quantum threat is a quantum computer that can break Shor's algorithm, which is essentially going to break encryption keys that we use today. And that's and that is the value that quantum computers can bring to a malicious actor. And again, it's because part of it is because the algorithms that, or the keys that we use today are based on classical computing. So Shor's algorithm shows that they can be broken. But if you use something called a quantum random number generator to develop your keys, that is not something a quantum computer can hack because it's based on true randomness. And that is one of those technologies that we're looking to deploy on the energy sector. It's those quantum random number generators for key encryption, as well as post-quantum cryptography and quantum key distribution. Although DoD is not a fan of quantum key distribution because they claim that there's a problem with authentication. On the energy sector, we don't have that authentication problem because we have our set points are set. The control center is where it is, and the substation is set. And so the keys can be embedded there from the very beginning, and we know that they've already been secured. So we don't have we have our use cases allow for quantum key distribution to be deployed without the concern that DoD has. So that I just want to put that out there because I think there's been a lot of bad press around quantum key distribution. It's from the standpoint of DoD. So although there's a lot of work that I am interested in doing with DoD, that is one area we're not going to collaborate on because our use cases do vary there enough that it allow, we have different perspectives. So just going back to the quantum, to the use case number 3, where we're looking at quantum secure communications. Again, quantum random number generators, going forward, that's what I think people should be using, and that's what we're going to be asking the energy industry to continue to use. Post-quantum cryptography, NIST is not developing, but they're not certifying, but reviewing the algorithms out there and trying to determine which ones are of meet muster, let's just say. And then we're looking at entanglement as another feature for security. And Topash, I'm almost done here. If you need, are there any questions? Because I know I can't see everyone, so. I can't hear you, Topash.
Sorry, I was speaking on mute. Yeah, no, I think we are all ears listening to you. I mean, we do have questions, but take your time. I think this is very informative information.
Great. Well, so to sort of summarize things, why we're interested in space-based quantum. I mean, I know some people think quantum is already hard, Rima. Why are you taking this into space? There's a lot of value. We're going to do both. And there's no reason, we are right now doing fundamental science research. But just because we're doing fundamental science research, does that mean we shouldn't be doing applied? No. Where we can do them in collaboration or in parallel. And we are doing it because, as I mentioned to you before, we already have atomic clocks. We already have MRI machines. So why can't we use these technologies for more than that? And that's the argument that we're making. And then at the same time, there are these sites on what else can we do, and so there is this long-term vision. Mm-hmm. So we're doing fundamental science research. We're doing applied research in parallel. And the space-based activities really do provide a lot of value when you think about how we can explore the Earth in a more practical way and be able to find opportunities that we may not have been able to see unless we have a greater perspective. We talked about how we can use navigation and timing to be able to more precisely integrate mobile storage capabilities and how they and the opportunities there are amazing, because when you think about it, these applications can tell fleet owners what is the most valuable time for me to do, most valuable thing for me to do with my fleet or my assets right now. Should I be storing? Should I be charging, discharging, or running my errands, or doing the usual course of business? That's a huge optimization problem, and I think quantum computing today can help solve that problem, and more, and we have some partners looking into that already. I mentioned geothermal detection and imaging capabilities. I mean, it's an incredible opportunity for us to really understand this planet better, and how to use it better, and how not to hurt it, right? And then I also mentioned, the grid timing and applications, GPS synchronization across the various types of things that interconnect with the grid is going to become more and more critical. And then also from space, we have an opportunity to do a lot of remote imaging that could help California spot wildfires in areas that are so remote that nobody would have noticed it until it got too big. I mean, that alone, when you think about how much damage these wildfires cause, and the destruction that they bring, and how much it costs the government to then come in and bring things back to baseline, that the technology pays for itself from a taxpayer standpoint. So there's quite a bit of potential. So I did want to mention that there are, some people always ask me, are there opportunities for us to engage with the Department of Energy? I've listed here some things that have come in the past. There's some stuff coming out next week. So I was hoping that I would have been able to announce it today, but it's coming out on Monday. But there's some more collaborations and opportunities. Some of them are directed towards the national labs, but there is opportunity to partner with the national lab system in order to take advantage of some of the funding opportunities that are coming out from the Department of Energy. And we're always looking at ways that we can partner with the private sector, even in the absence of a funding opportunity announcement. And sometimes these partnerships, we make them public, we talk about them, we shine a spotlight on them, and then it inspires the powers that be in Congress to then fund those activities. So there's lots of different creative ways that we go about how we can get things done, and with and without formal funding. And then lastly, I mentioned some of these moonshot opportunities that DOE is pursuing. Obviously, putting quantum technologies in space on the surface sounds like a moonshot activity, but I'm always reminded of Feynman's famous quote, nature isn't classical. It's going to be hard, but he also said that we need imagination, and that without it, it's a terrible straitjacket. And so we do need to think outside the box. And if we don't, then we won't meet those moonshot opportunities, and we'll get something short of that. So that's the end of my presentation. I'm happy to take questions. And thank you.
Rima, this is phenomenal. The talk itself is phenomenal, and thank you for the perspectives. I mean, I have so many questions. I'm going to start with something high level, and then go actually something low level, and then go into something high level. Well, let's start high level. So, I mean, looking at your talk, it seems we are doing a lot, right? At least as a country, right? But if we go to conferences, then you have been there. We've seen a lot more has been done in Europe, in Asia, and other places. In your perspective, are we doing enough as a country on the quantum front, or do we have room to grow?
Yeah, I think there's always room to grow. And my concern here is that we are a little bit stovepiped in the US in terms of how the federal money has been deployed. And there's a few of us that are trying to break those barriers, right?
Mhm.
I think, unfortunately, the narrative has been to just focus on the fundamental science research.
Mhm.
And I'm not saying that's not important. I want to understand dark matter. And who knows what, what value that brings to us. It's something we could probably never imagine. Um, but at the same time, I'm also practical about, yes, we went to the moon, but we learned so much as a result of that, right? And we commercialized technologies as a result of that. You know, maybe some people don't like gym shoes that much, but we got that because we went to the moon, right? It
Yeah,
was part of
exactly.
the spacesuit, and there's value to that, right? And so let's not discount that, because we need these little nuggets of
Mhm.
opportunity, of commercialization, to keep the fuel going and prevent us from going into a quantum winter.
Yep.
So what I think we should be doing more here in the US is investing in the applied capabilities of quantum technologies. And that's what I'm focused on. And so I'm focused on it from an energy standpoint, but I'm also obviously building alliances with other sister agencies where I think we could bring value to them early on, where there's synergies with energy. So we could piggyback off of one another, because we weren't funded significantly to do applied research using quantum technologies.
Mhm.
And so we're being creative to leverage the resources we have to do it in spite of that.
No, that's great. And now the low level question. So I was impressed hearing from you that DOE can deal with NISQ computers. So when I think of NISQ, I'm thinking of not the annealing types, I'm talking about the gates types of stuff, right? So the quantum gates technology. So I want to get a sense from you. Your feeling is we are more or less ready with at least commercializing or using both annealing as well as the gates technology. Is that where you're coming going
Yes,
from?
yes, I agree.
Yeah.
And then because we have some researchers that have developed um, algorithms for contingency analysis, and it looks
Yeah.
good.
Okay. Yeah. I mean, if there is anything public that you want to share, we'll be happy to look into it. I mean, in my own research, we are doing some work using gates on cancer detection, basically. I mean, it's a image processing project on cancer detection. We'll have something published in IEEE, probably the next conference when we have in August. Yeah. So no, it's impressive time for this overall. One other thing that I wanted to bring into light is you talked about atomic clocks, right? Generally, the size of the atomic clocks are pretty big, generally. I had the opportunity to meet somebody from Caltech, and the gentleman is here, Raj, who has built an atomic clock, and his size is that of maybe a quarter, uh, as a US 25 cents quarter. So I'd like to bring at least first Raj to this and ask Raj. I would like to give you an opportunity to ask your question to Rima about atomic clocks and how do you see what you are doing there. You're on mute, Raj.
Can you guys hear me now?
Yes, sir.
Awesome. Yeah. And hi, Rima. This was really interesting to hear. Quite frankly, we had not even considered the aspect of bidirectional storage. So while we had heard about NASP, that's the National North American Synchrophaser Initiative, we just took it in terms of more renewable energy sources. So that was really amazing to hear about. To give some introduction, this our venture is sort of a collaboration between some research emanating out of NIST and Caltech. The clock part was coming out of John Kitching's group at.
Raj, I'm having a hard time hearing you.
Okay.
Um,
Is this, wait, let me put up the gain. Is this better?
it's a little bit better. Yeah.
Okay. Yeah. So the part of our clock tech comes out of like John Kitching's group from NIST. and we are also working on the Caltech end. We are working on spinning out other research that is coming out from LIGO, because that's another place where we felt that the learnings were not translated to industry. The part that I want to understand is, while I see DOE has interest in atomic clocks, I wanted to understand a bit more about the kind of support that DOE can provide in this regard, because a lot of these large synchronization based projects need to show implementation, which I don't know if we could do alone in any way. So
They need to show what?
implementation in the sense, how do like in terms of showing that this can be applied to the grid, is there support from DoD that can help us demonstrate this kind of capabilities?
Yeah, so in the Office of Electricity and the Office of Cyber, Energy and Security and Emergency Response, CSER is the acronym. PNT is a big part of what they're looking into. And, when they put out funding opportunity announcements, they don't always use the word quantum. Mm-hmm. They're going to start now. So it'll be more clear, but position, navigation, and timing has been a part of our mission. And there is a huge collaboration right now across all the various federal agencies to focus specifically on PNT, and DOE is a part of that. Yeah. And I've been informing that group, and what they've realized is that we need to move away from GPS and look at distributing quantum sensors for PNT. And so that's going to include it's coming, but you're going to see DOT, DOD, as well as DOE significantly investing in that area. I sort of mentioned something's coming out next week. It is directed towards the labs, mm-hmm. but the labs are encouraged to work with industry. And it's a start that is where it's like a small seed amount of funding to basically signal to Congress, we need to formalize this, we need more.
I had a quick follow-up question. Would you be aware about the kind of clocks you're looking at? Because even in the optical clock range, there can be a quite a large amount of variability. Are there any specifications that you guys are interested in specifically?
We're leaving it open. We don't want to be prescriptive.
Yeah.
Yeah, because we want the best ideas to emerge as opposed to being prescriptive of which ones we're rooting for. So there's flexibility here. And we're also going to be doing an RFI, so I can say this publicly, a request for information. So there's a small amount of funding coming out next week. It's directed towards the labs. So it's not public yet, but I feel comfortable. It's Saturday to mention this to you guys. And then there is a request for information that we'll be putting out that is specifically on quantum for energy. Mm-hmm. And that's where we're going to ask these types of questions, which is, what do folks think? Should we be focusing on specific types of quantum sensors for PNT in the energy sector? And if so, which ones? So we're going to ask those types of precise questions. And if you guys have thoughts on what kinds of questions you wish people were asking, send them my way. The time right now is good to do that.
Yeah, so I'll probably connect with you after this, because I think there is a lot of opportunities with DoD, DOE, which we had not considered before, because primarily when PNT comes up, the conversation goes towards DoD, mm-hmm. And this is something we would really love to explore further. And I guess Rishti will be a great person to get in touch with you and discuss further on this topic.
Absolutely, yeah. I think I had my email up on the slide. I'll put it in the chat, and folks are welcome to reach out to me. I really would love to know what questions you guys have. And I think this request for information that we're going to be putting out, if those questions align with what we're interested in, we'll put them out there. And it's really exciting. I get excited when we do these RFIs because we create this beautiful, Congress pays attention to them.
Okay. Mm-hmm.
Right. And it was through this, it was because of an RFI that Congress took interest in bidirectional electric vehicles and then explicitly asked DOE to support them and create and expanded the tax credit to include bidirectional electric vehicles explicitly. So it all came out because of an RFI, and a few workshops here and there, that we casually invite them to, but it all helps. So so I'll put my email in the chat, and would love to hear from you guys.
Absolutely. Thank you so much. This is
really
Raj. Exciting.
Raj, I'm hoping you can, you and Srishti can come one of these days on this and talk about the quantum sensor. So I think that will be a topic that everybody is interested in. We'd like to understand the nuts and bolts.
It's so underappreciated. Everyone talks about quantum computing and then they talk about security as using fear as a tactic. Sensing is actually, I think, what might change the world. Sooner, because it's going to give us perspectives that we don't have, that'll help us make better decisions and choices.
You're not going to get any disagreement from me on that, especially because I have a commercial interest in this. But I agree, because like as we did in LIGO, like that's the best sensor that we have in the world today, and just scientifically we saw how much we gained from it, and we're just beginning to see all the commercial possibilities that exist from that. So far we have just thought of, okay, better quality lasers, better quality mirrors, and so on, but there is way much more that exists just out of immediate commercialization of that we've been working on.
Raj, do you want to just say 1 minute about LIGO? When you're saying LIGO, I mean, it's a Nobel Prize winning from go ahead, talk about it a little bit. For a second, for people to understand what's LIGO.
Quick introduction. So LIGO is basically a 4 kilometer by 4 kilometer a sensor, it's extremely huge, and it is used to measure gravitational waves. And in the process of doing this, they came up with new technologies of how to do the most precise sensing in the world, because gravitational waves are very, 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 very weak. Now, in that process, we also came up with other ideas on how to do very small measurements of other fields, which I think just sat in the LIGO document, like the LIGO document base, and nobody really explored it. But this is something which I am doing my PhD on, and that's where all of this comes in.
Yeah, sensing and imaging is really interesting, and what a lot of folks don't, I think, appreciate is that fundamental, like quantum behaves differently in space than it does here on Earth because of gravity. And so we get different results when we do experiments in space versus on Earth. So, we might be banging our head, like, why isn't this doing what we wanted to do? Or we're not getting certain results here, but then we get different ones on the International Space Station. So it's another reason why we should be exploring quantum in space. Especially from an energy standpoint, right? Minerals and things may actually behave differently in space. The other thing, in terms of imaging, quantum sensors have the capability today. We've seen experiments where they can see around. You can use a quantum sensor to see around a corner, right? Because it's using reflection of water particles in the air to be able to create different types of mirrors. And so deployed on vehicles, it could prevent car accidents from happening because somebody's running a red light and your vision was blocked because of a building. That won't happen. But then there's also the capability to use these quantum sensors to be able to see through walls. So you can, firefighters can use this to save lives, but then they also can use it to spy on people. So there are also these ethical conversations that we're having, which I know is beyond the scope of this, but
Yep.
what I'm trying to highlight is that quantum sensors are a big deal.
Yeah, and then on that, Rima, as I might mention, I'm writing that thing on governance, AI governance, both in the classical and the quantum world. So that's something that I'd like to hear your thoughts later on. I'll connect with you offline on that. Yeah, because we are going into an uncharted territory there, basically.
We are. It's
Yeah.
exciting and scary all at the same time, but we're humans, so we're going to do it anyway, right?
We are going to do it anyways. Yeah. I'm going to take one question. I know we are at time from the audience. So anyone wants to come out of mute and ask your question, I'm going to just keep it open for
Hi, it's Pratyush. Can I ask a question?
Sure.
Yeah, it's not related to quantum. Like, I just wanted to know about like image, and I have more interest. Like, I'm a fresher, so I'm learning. I just want to know the scope of image processing and NLP. Like now NLP is going on, but what about image? I mean, other than self-driving technology. So where could that be used, implemented?
The imaging capability?
Yeah.
Well, so I mentioned imaging, we can do subsurface level analysis and be able to identify caverns underground where we can store carbon, find geothermal, or do more precise oil and gas. We can see through deeper depths underwater, which can then help us do offshore siting at a more effective cost. A big part of the cost in offshore wind is the siting process. So that could be also remediated or mitigated, right, to a degree.
Yeah.
So yeah, so exploration, and then I also mentioned being able to do imaging to identify wildfires in remote areas before they get too big. A big reason why these wildfires get out of control is because they're
because they're
identified
not
too late.
noticed or identified too late.
Yeah, and it just because it's in remote areas where there is no human to know about it. The other thing that quantum sensors can help with is climate change tracking, right? We can also use them for carbon sequestration, like to be able to measure it. Like there's this whole market emerging on measurement and verification, and sensors can be another way to do that measurement more accurately, and also to detect changes in methane leaks. So we're also looking at quantum sensors deployed on pipelines to do better tracking of leakage. And if we're talking about building hydrogen infrastructure, we sure as hell want to do better measurement and leakage prevention, because that's scary if that stuff gets into the atmosphere. It's scary.
Yeah, I can understand. Yeah, thank you. I understood. Like, what about if a fresher wants to, like, I'm a fresher, so if I'm interested into quantum, so what will suggest to start with? Like, I mean, how will you progress on how to start? Like, according to you, just maybe a few suggestions.
So you're saying if you're new to quantum, how do you start looking into quantum?
I have worked with different projects related to NLP, images, and did few more steps, maybe building apps and stuff, but I don't have much knowledge regarding quantum.
But so the use case that you're most interested in is imaging?
Yeah.
Okay. So that'll are there certain markets that you're more familiar with?
You mean like maybe health, or like currently also interested in self-driving? So yeah, working on two projects basically.
Okay. Yeah, no, I see the temptation there. Yeah, I mean, from a health standpoint, obviously the market already exists because of MRIs. And so there's interest now in doing imaging using quantum sensors that don't require the same kind of cryogenics. and machinery that is necessary to do MRI, to do the type of work that MRIs do. So that is a huge opportunity right there, obviously. And then from the energy, yeah, from the energy standpoint, the quantum sensors could replace, some of the technology that we're using today for self-driving cars. So that one's obvious. I guess right now, I think that from a market standpoint, what we're about to embark on is a benchmarking exercise to really look at the swap C, the size, weight, and power and cost relative to the next best alternative, to figure out where the near term, where the biggest bang for our buck will be. And we are still trying to figure that out. Because there is just so much, the possibilities are pretty wide. And so we're trying to figure out what to attend to with the few resources that we have. So that's an exercise from an energy standpoint we're just now embarking on.
You are like scratching it on subscript. I mean, like you are just starting it. I mean, beginning. Yeah.
We have an idea of all the different types of sensors that are where there's been research and what all the various use cases are and what the various TRL levels are. But the TRLs are not refined enough. And what the data that we're missing is how much improvement in the swap C can we achieve, and then how would that compare and compete with the next best alternative, which is the status quo in a given use case.
Yeah, I can understand what you're saying.
Just wanted to thank you, Pratyush, for your question. I know we went 8 minutes above time. I wanted to thank Rima for her time. And really appreciate
thanks a lot. Thanks a lot.
Really appreciate for her to come here and spend some time with us. So Rima, thank you. It was very nice having you here. Really appreciate it. And looking forward to see you in other forums as well as here as an audience if you want to ever join us.
Yes, I would love that. Thank you. And apologies, a big storm came in, which was making it hard to hear at one point. But
we should do something for the weather as well. Get it under more control.
I know. More precise quantum sensors would have told me to shut the windows. Anyway, thank you all. It was a pleasure talking to you. Have a great rest of your weekend.
You too. Take care. Bye.